Okay, let's get going. So despite the title, which talks about relational and COBOL, this is actually going to be a technical talk, which means I will get rid of this crap. And I'm socially distanced, so I can get rid of that crap too. So kind of fun to be up here. So today's talk is going to be a little bit different than the average reInvent talk. This is not a talk. I'm not pitching a product. I'm the CTO of this company, but I'm not pitching that product. I actually had an experience a couple months ago that I'll get into, which made me think about technological change, and I'm going to talk about that today. This is not a hard sell. This is all for you to listen and think about the technological changes that you're going through in your lives and in your companies, and to reflect on them. So today, the first thing we're going to do is I'm going to give a little bit of an introduction of me and why you might want to care about listening to me or not, and I'm going to state my thesis, very mathematical. Then we're going to get into some of these other topics you see here, and God forbid, I'm not going to waste your time by actually quoting them to you right now. You can all read. So the first thing is, why am I up here? I have been dealing with data since I was 14, and I'm way older than 14 right now. You can do the math, okay? And during that time, I have worked for a bunch of companies, and they've been wonderful companies, including AWS. I've presented at this conference as a speaker when I was general manager of AWS in Aurora for a while. And during my career, I have either used or built databases as the entire thing that I have done. Now, right now, I'm on a build phase, and I'm really excited about building databases. But the reality of the situation is the experience of the using databases side actually helped just as much. So let's talk about technologies replacing each other. And that's going to be the theme of this talk today. So here is New York in 1900. And this is a picture, and there's not a car in sight on that street. It's all horses. And in 1900, there were 21.6 million horses in the country for 73 million people. Now, something big was about to happen. And by 1911, 4,000 days later, which doesn't seem that long, by 1911, that street was full of cars. It's amazing. So it's not just the technological change of horses to cars. It's the underlying thing that went behind it. And by the way, we're sitting here at AWS reInvent, and think about the sea change that has gone on since AWS launched the cloud. It's very similar to this change. It wasn't just, I'm hosting my VMs in the cloud versus on-prem. It's the entire infrastructure around it. It's data centers, it's networks. Well, for this change, it was all about cars replacing horses. And before that, internal combustion replacing steam, and steam replacing water wheels. You can read this. And what made the technological change happen? Economics. People found it easier or better or cheaper to do something. And by the way, trust me, I am going to get back to relational and COBOL. Look at this graph. This graph is unbelievable. And I started this talk about 4 months ago with my technical advisor who did an awful lot of the research for me. Thank you, John. And you can see on this graph, on the vertical axis, you can see the units of cars. It's a log scale. I'm a nerd, so I get to use log scales in my graphs. And years across the bottom. And the data is actually the light line, and then there's a smoothing fit curve, which is the dark line. And you can see that over a space of about 20 years, the entire US economy changed over. Now, one thing that was amazing about this as we did our research together was the slope of that smooth line. I mean, it just looks too real to be true, right? What could that be? That's actually the growth of the US economy during that time. Now, think about what we're doing at this conference. The economy of this country is strongly based on cloud computing. It's strongly based on IT. And COVID has done nothing to change that. In fact, it's accelerated that. So if you look at this, you look at a change that probably felt unbelievably fast at the time, 20 years. But now you can look back and see how it progressed. But God forbid, enough about horses. We're not here to talk about horses. Okay? What we are here to talk about is what causes technology changeovers. Why do some technologies hang around? And can we predict these things? So think about, for those of you who are developers, think about which technology stack you're using. Think about how you're programming. Think about your company and how culture change occurs. Culture change is huge. Can we predict these changes? And by the way, I'm going to take a pause here. Paul, you never started the countdown timer, so if you could start the countdown timer, that would be awesome. So I very, shall we say, controversially put COBOL in the title of my talk. Now, why did I do this? I talk to more than one CTO a day. I've been at MongoDB 16 months. I've talked to 450 C-level executives. And on one of those talks about 4 months ago, the executive said to me, Mark, you've been in relational for so long. I can't hire relational people out of school. No one wants to work on relational anymore. I said, what? He said, yeah, and by the way, the people who are at my company, they keep telling me they will quit if I keep making them work on some of those commercial databases, Oracle, SQL Server, et cetera. Instead, all they want to do is work on new technology. And so he said to me, Mark, is relational the new COBOL? So I can't take credit for this title of my talk. That CTO ran a team of 75,000 people, and he was having trouble hiring people for relational. So let's talk about COBOL. COBOL was born before I was, born before, I bet, most of you in the room, and it is the common business-oriented language. It was dictated by the DoD in 1959. It is an amazing language. It lets you do a lot of things. And believe it or not, it's still alive today with the COBOL 2014 standard offering object-oriented programming and inheritance and things like that. So it's still widely used. And I'm going to ask you, really? You're going to say that's not true. Look at what's on the screen right now. New Jersey had a system to process unemployment claims. And that system during COVID, this is from April of 2020, that system during COVID started getting 15 to 20 times the number of requests they had ever gotten before, and it started to fall over. And they dug into their system and they found out it was all old COBOL code, and they literally had no one to program it. So they put out this public plea for people to come and work on it. Now, you might say, well, that's because COBOL's dead. Well, you know what? It's actually not. And this is a statistic which blew me away when we did the research for this paper. Of the Fortune 1000 and the Russell 2500, and I did not believe this statistic, so we researched it about 7 ways from Sunday, 60% of those enterprises still use COBOL. Now, what percentage of enterprises use relational? I'm guessing 100, okay? Probably maybe 98%, something like that, somewhere in their enterprise. So it's still widely used, even as of today. And in fact, there's 220 billion lines of active COBOL code and 1 to 2 million active COBOL programmers. But no one's using it for new development. And in fact, this statistic I also researched heavily. It stops at 2004 because no one's really been tracking this statistic since 2004, since it became relatively irrelevant. And now you look, there are 80 to 100 billion lines of new code. I don't know how to believe this statistic, but it's the best I could find. And this second statistic I know very well. There's 23 to 28 million active developers in the world. Now, for those of you who are whipping out your iPhones and doing the math, that's 4,000 lines worth of code per year per developer, or 20 lines, or 15 to 20 lines a day. So, just for the fun of it, and then we'll move back to relational. This is hello world in COBOL. If it's 20 lines long, it's about 19 lines longer than it needs to be. And it's just not very exciting. And yet, you know, there's 1 million people programming this every day. New graduates have moved on. New graduates, the age, and this is what that CTO told me, I was waiting for this slide to say it, because this CTO has 75,000 employees, they have enough data to do big data. They said that their age of their COBOL employees is going up by 0.9 years per year. That says something. It's kind of scary. So here's the disclaimer part. I kind of like COBOL. I've programmed in COBOL. I love relational. I was at Oracle for Oracle 5, 6, 7, 8. I ran Aurora and RDS. I love relational. I'm not here to slam relational. However, I am concerned that COBOL is a technology that's been used for many years, still alive today, but literally no one who knows what they're talking about has any interest in developing new apps on it. And now we get to the thesis of the talk. The thesis of the talk, which I believe after doing all the research, is that relational databases are a technology which will also live, just like horses, just like COBOL, but they are not the right place to develop new applications. And I say this as the CTO of MongoDB, but there are also other non-relational stores out there like Cassandra and Couchbase and Dynamo and all those things. I think they are all better places to develop new apps than relational. So there's our intro and thesis. But it's fun to actually think about how data developed. You know, relational wasn't even close to the beginning of data. The 4 things on the left, cards, ISAM, VSAM, some of you in the audience have programmed with these, I'm sure. They all sucked. If you go back and you read articles from that time, even the people of that time knew that these were bad ways to model data. They don't even say this is the right way to model data. They say this is the best I have in 1965. And so they all faded out, and they were very frustrating. But in 1970, this amazing guy, a researcher named E.F. Codd at IBM, came up with this paper, and it's called A Relational Model of Data for Large Shared Data Banks. And it's worth reading. Just Google it and read it. And what he did in this paper was truly revolutionary. Note that this was 51 years ago. He established relational algebra using set theory, unions, intersections, projections. He established a mathematical basis for processing data, which had never been done before. And that was amazing. He also was very concerned about space efficiency. So I looked up in prep for this paper. At the time he published this paper, a 5 megabyte disk drive was about the size of that podium, and it cost $225,000. And that's not in today's dollars. That's $225,000 in 1970 dollars. So space was at a premium. But he also thought about something else. He thought about not duplicating data because now you have 2 sources of truth. And so he came up with this mathematically pure thing. He combined that with flexible normal forms of data, which is the way to project data, the way to merge data, the way to join data. It's all there. And it's really cool. The problem was he completely, if you read the paper, ignored the efficiency of data access, the efficiency of inserts, the efficiency of querying. It was this beautiful mathematical proof that really didn't apply to the real world. Now, because space was so important, it was okay, and people built a lot of stuff on it. Now, the one thing he didn't come along with was a language. Now, he had his own language, and he wrote a separate paper about that, which you can look up. And he wrote that he believed that we should have a language. Amusingly, E.F. Codd is credited with SQL. That's in the myth, the urban myths. The reality is he wasn't actually a fan of SQL, and he devoted an entire chapter, chapter 23 of his book in 1980-something, I can't remember. He devoted an entire chapter to why SQL did not represent what he had had in mind in 1970. Ignoring that, as Larry Ellison tends to do, Larry Ellison came out with the first commercial version of SQL, accessing a relational database, in 1979. And frankly, stole the march on IBM, which is pretty amazing when you think about disruption. So now we had our very first way to store data, and everyone agreed on it. And if you read the papers, like I did for this talk, in the 1970s and early 1980s, this was viewed as unbelievable. And sure enough, people just started throwing data in. This table on the vertical axis is Zettabytes, which you can think of as just an awful lot of bytes. Okay, it's above exabytes. Okay, and on the horizontal axis, it's years. Now you might ask, Mark, your talk goes back to 1970. No one was actually keeping track of the amount of data in the world before 2010. The only estimate we could find when we researched this paper was that IBM had an estimate that there was 1 exabyte of the world in all digital systems put together in the year 2004 or 2005, which is unbelievable. And so as you can see, this went up, and there's so much data. And in 2025, IDC projects that there will be 36 zettabytes of data created. This is row and column data. However, it turns out that from the dawn of data time, whatever that means, from the dawn of data time, most of the data, ranging between 70 and 85%, depending on the source, is not actually row and column data. It's heterogeneous data. It's documents. It's audio files. It's video files. It's data that doesn't conform to any standard. And in fact, IDC, on the same scales as before, IDC estimates there'll be 182 zettabytes of data produced in 2025. Now, I know you're sitting there wondering why you came to this session and wondering why I'm talking about this. We have to process all that data. Chips have to process all that data. Otherwise, what good is it? It just goes and sits in, S3 archive or something. It's not useful. And so we have to process it. So let's talk about processing it. The next thing you're going to wonder is, how did I manage to get the words bloodless coup onto a slide at reInvent? Well, I'll show you. It's actually kind of fun. In 1965, Gordon Moore, the co-founder of Intel, and a truly brilliant person, came up with this observation. Now, he did not call it Moore's Law. Other people decided to call it Moore's Law. And it said, and this is one of the few slides I'll read to you, the number of transistors in a dense, note that word for the next slide, a dense integrated circuit doubles about every 2 years. Kind of cool. He equated this to the performance of a chip and the ability to process data. And this is very relevant for what's been going on the last 10 years, which I'll get to. Now, God forbid, it sure looks like a law. You take his 4 data points, 1959, up through 1965, and it sure looks like a law. But I mean, he totally went out on a limb here with only 5 data samples, right? And I will point out to you that 2 to the 6, last time I checked, is 64. So here he is making this prediction when there's going to be 64 components on a chip. Well, all of us are in this room today because of the unbelievable ingenuity of the chip manufacturing industry that has managed to keep Moore's Law running for 56 years. On the graph on the left, you'll see performance, and you'll see log of the transistor count, another log graph. And on the bottom, you'll see years. And the red lines are GPU, and the green lines are CPU. And amusingly, they track somewhat close together, even on a log graph. Now, I'm not going to read all the stuff to you on the right. It's no fun. The net is that Moore's Law, which is the ability of computers to process data faster, has actually been running really strong for 56 years. It's the party that never ends. It's awesome. It just keeps going. Transistors per chip. The problem is that if you actually plot spec-int performance, which frankly is a very forgiving test compared to actual business workloads, it started dropping off in 2004. And so what did the chip companies do? They went, oh crap, what are we going to do? How are we going to keep up with Moore's Law? They invented multi-core chips. And so they did that because they saw performance starting to fall off. And now you can see people adding 2-core chips, 3-core chips, 4-core chips, 8-core chips, etc. And they were able to kind of keep up. But here's the funny thing. They only kept up on the number of transistors on a chip. They didn't keep up with the performance or the ability to process data. I already said that about 2004. So we transitioned from Moore's Law, and here's the bloodless coup, to Amdahl's Law. Now, a lot of you out there are saying, oh my God, what's Amdahl's Law? Amdahl's Law is the statement that you can only speed something up by the degree to which it is parallelizable, and in this case, by adding multiple cores. And you can see 2000 through 2015, the red line is 2-core chips, the black line is 4, I think yellow is 8 or something like that, maybe red is 8. You can see that each additional core contributes less speed up. And in fact, Amdahl's Law states that if you have something which is only 50% parallelizable, you will not be able to speed it up. I'm a database guy, okay? What do databases do? They lock things in buffer caches, they read stuff from disk, and they wait for it. They do all these things. They are fundamentally very, very hard to parallelize. So what we've seen is we have seen the actual performance of relational databases, and even any database, even MongoDB, on single machines has not kept pace with the number of transistors on the chip. And this is important because relational databases, unless you want to pay Oracle or Satya an awful lot of money for always on or for rack, they're only single primary databases, which means you can only take writes on a single node. And this is the core thesis of the talk, that single processor or many processor machines running parallelized workloads are slowing down. We need a new technology. Let me just go back to that data slide for a second. In the upper left, you can see that little data slide from about 15 slides ago, and you can see a log graph of data, zettabytes, on the right, and then you can see, I decided to add under so that none of you called me out on the internet, IDC has actually revised their estimate down to 127 zettabytes by 2025. I actually disagree with it, but I didn't want any of you to call me out on it. Now, if you take the most favorable performance graph, which is a straight line graph rather than following the curve, you can see that computers cannot keep up with the amount of data they are being asked to process. So, the data explosion, plus the transition from Moore's law, which is becoming irrelevant, to Amdahl's law, which is parallelism, is resulting in a growing performance gap. So now we've talked about hardware. Now I'm going to transition to talking about software and why relational is having issues. And I decided to title it Pay Me Now or Pay Me Later. Horses and cars solve the same problem, transportation, but they solve it very differently. If I was going to take a horse from Missouri to Oregon, if I was going to take a vehicle in the Old West, I would want the horse because it refuels on the way. But for pretty much every other reason, including comfort, I would rather have a car. So they solve things differently. Relational and non-relational. And I will confess to you that when I came to MongoDB, I did not understand this fact. And Dave, my boss, is sitting right over there in the audience, and he's probably going to go, wow, Mark, I can't believe you said this. I did not understand the fact that MongoDB and non-relational stores are distributed systems that happen to process transactions really well. Relational databases are transactional systems that scale out for shit. That's just the reality of the situation. Any of you in this audience who are trying to scale relational databases know that scaling is their Achilles heel. And I had to learn that very painfully when it came to Mongo. So let's see, does relational do a better job, more efficiently, and easier? I'm going to make the thesis that non-relational is more CPU, network, and I/O efficient on storage and retrieval, especially for modern apps. On the left, you have a library. And it's run by the Dewey Decimal System, and everything has its place. And when a new book on the Civil War comes in, you move the books aside, and you move some pointers around, and you shove the book in. On the right, you have a picture of an early Amazon warehouse, where when products used to arrive at Amazon warehouses, they used to take the light bulbs and put them with the light bulbs, and then they'd take the razors and put them with the razors. And they eventually figured out that was really a bad idea. When the light bulbs came in, they just put the light bulbs on the nearest empty shelf and noted down where they'd put them. Well, that's relational versus non-relational. When data streams into a non-relational database, you just index just enough of it to know how to get it back, and you move on. Which is why relational stores can easily take millions of writes per second. I was talking to a customer this morning who is running a 90-shard MongoDB cluster with 5 nodes per shard, 450 nodes all cooperating. And they're running on over 800 terabytes of data in a single database. You just can't do that with other systems. Now, other non-relational systems do this too, by the way. And so that's the important thing to note, is that we've changed. When you take in data into a relational database, let's say it's an order with order lines and some data, you have to unpack it. You have to go put the order lines in the order line table, every single one with an index lookup. You have to put the order in a table, every one with an index lookup. You might have 20 or 30 or 40 cache hits or IOs to store one thing that came in from your data provider. And many of you, as I've talked to this week, You've talked to me about how getting data from your partners or from other parts of your business is fundamentally the limiting factor of how fast you can do things. Not only that, getting the data out is the same thing. You have to put it all together. You have to traverse all those indexes. You have to take locks. Oh, wait, what do locks do? Locks slow down your database, slow down your chips. Now, there's something I'd like to address, and I'll go on the record here. MongoDB, when it first came out, kind of talked a lot, as did the other non-relational stores, about how schema didn't matter. And it was so flexible, it was wonderful. That's not actually true. Schema matters more in non-relational because you don't have this mathematically perfect engine underneath which is covering up all the sins of you not understanding your data. So when we work with customers, we help them understand their data really, really well. And they're able to do things where their databases run 5, 10, 15 times faster because they've understood their data and they've designed a really smart system. And so again, all data is pre-normalized. However, in the non-relational system, it is absolutely true that if you do have to do a join, or in MongoDB, a dollar lookup, it can be more expensive, which again is a good reason to know your data well. So I talked about all that data, and I talked about how much is coming. Enterprises have lots and lots of data. I told you about that enterprise that has an 800 terabyte database. And we have lots of those. Typical storage costs, even on my favorite relational database as a service that happens to run on AWS, that I used to be the general manager for, are around $20,000 per terabyte per year. And though my customers tell me that they can get 2x or 3x efficiency, for the purposes of this talk, I decided to say that maybe non-relational is only 25% more efficient, resulting in $5 million per year per petabyte savings. And that doesn't even count the CPU savings. That's just the storage savings. Your mileage, of course, will vary. Point number 2, relational is easier to program against. There's just no doubt about it. I don't know when it became okay to think about my data the way it is on the left. That's not how I think about my data. I don't think about it with all these one-to-many relationships. I don't do math. I don't do set theory. I think about the way it is on the right. I think about it in one document, and I process it. Now, here's the interesting thing. When relational databases were produced, programming languages were very much like the thing on the left. And so the impedance mismatch was not that high. But now, programming languages are very much like the thing you see on the left right now. You can put multiple types together, you can embed arrays, you can embed subdocuments, and you can just program to your heart's content. Unfortunately, that thing on the right is still going to make you break it down. And so we've created these things called object relational mappers. And what they do is they try to be very clever, and they figure out how that thing on the left maps to the thing on the right. And when they get it right, it's good. When they get it wrong, you get terrible query performance, missed plans, table scans, and all sorts of other things. And the bad news is you can't actually control it. Now, I said this in a talk earlier this year, so I'll say it again. 68% of downtime when I ran RDS and 65% of downtime when I ran the systems at Grab was due to bad deployments. Of that, over 25% of that downtime minutes were caused by relational database plan misses and other problems. And that's a big amount. So why not have your database store things like on the right? Single I/O, natural, easy to program, easy to debug. Now, I did an informal survey earlier this week and at a prior conference where I asked people, how do you insert a new data element into a relational database? And all these people said, oh, it's alter table, add column, var int, whatever you want to call it. It's all good. And I said, oh, that's awesome. So, and a lot of them said, well, yeah, but I have to log a ticket with my system administrator because last time I added a column, production went down. And we all know that. I mean, I can't see you because the light's, but I know many of you are smiling behind those masks because you've had the same thing happen to you. Well, with relational, that's what you do. With document databases like Mongo and others, you just add it to your code and it adds it to the system. That's it. There is no alter table command. It just happens. So it's fundamentally easier to program against. Now this slide gets a little bit of an eye chart, so I'm going to skip reading it to you. There's another problem. SQL was like a proof, a geometric proof. And geometric proofs love to make statements, and they're declarative. And SQL's declarative. I would like the set of all couches that were sold in Missouri last week to people who are over 25 who own luxury cars. That's a great question to ask. But that's not how programmers work. Those of you who program in the audience, we're like, oh, heck, let's go figure out Missouri. Now let's go figure out couches. And they're iterative. And so MongoDB, and this is an actual plug for my product, MongoDB has these things called aggregation pipelines, where rather than having a 60 or 70K SQL statement that you debug by resubmitting it again and again and trying to figure out where the results are broken, you actually do it in stages, just like you program the rest of your code. So non-relational also scales easier. And this slide, which I'm about to show you, is a slide that I've actually been working on for about 20 years. I started 30 years, worked on it at Oracle. And on the left is how people scale their applications when they know that they're running out of speed or running out of juice on their big iron. They actually start sharding at the application level. We're going to put all the orders for Alaska in this database. We're going to put all the orders for California in this database. And all the applications are going to talk to each other. The problem with that approach is that you now have to become expert at deploying your apps. You now have to figure out how you're going to shard. You have to do all these things. And that's why those two little red arrows are saying this is a really bad model. So then, when I was at Oracle, we thought we would solve this problem by producing Oracle Parallel Server, which later became known as RAC. And we decided that if coupling was good, let's do it everywhere. So we coupled at every layer of the stack. And that meant caching, that meant lodging, that meant storage. We basically tried to produce a single system image. And those of you who run Oracle RAC know that while this is theoretically a good thing, it is an operational pain. And Larry has made it very, very expensive. In fact, Oracle costs twice as much on every cloud other than the Oracle Cloud than it does on the Oracle Cloud. SQL Server did the same thing in 2018. Not very friendly for those of us at this conference, by the way. So this idea, which does give you high availability, is incredibly expensive, incredibly proprietary, incredibly complex. So Oracle realized this, and with Oracle 7, they tried to introduce two-phase commit, and that's kind of like the picture on the right. Unfortunately, they got it wrong. Two-phase commit was incredibly complicated to program, and no one used it. And so RAC, took over. Well, if you think about the NoSQL solutions out there, the NoSQL solutions are like the thing on the right. You let your apps not know about the database, which is good. That's what all those green lines mean. And you only tie together at the logical level. What's my API? What's my query? How should I distribute my query? And you have some layer of intelligence at the top that does not scale linearly or superlinearly with the amount of data you're processing. In fact, it scales sublinearly if you structure your queries correctly. And so this is what MongoDB and non-relational does. So it scales easier. And many of you have had the unfortunate or fortunate experience of having your app be wildly successful. Now, when I grew up, everyone was running departmental computing, and having my app be wildly successful meant I might have 10% more usage this week than last week. On the internet, being wildly successful means I might have 50x the amount of traffic. We had a customer recently, who I won't name, but they were running about 250,000 transactions per second, and they got featured in the media. And within 3 days, they had to scale to 1 million transactions per second. And they just did it. And they did it using the architecture on the right. And this is one of the reasons why relational is having problems, because as we all know, when you try to scale a relational database, the best way to do it is up. I was talking to a customer this morning at the restaurant, and they're distressed because they're running Postgres, which is a great relational database if you're going to run relational, and they're running the biggest iron that AWS offers. And they literally don't know what to do. They're in a situation where, like, I can't scale up the iron. Do I move back to on-prem? They don't know what to do. And so that's why they're talking to us. So these are the reasons that this technology, which was so magical 51 years ago, is no longer magical. So let's go through a summary of what I've said today. First off, non-relational technology has easier schema design. You just build it in your code, you can be a microservices company, you can deploy. So there's lower setup costs. On-demand normalization, far lower I/O costs, as I've talked about. Co-located data, far lower retrieval costs. Simplified scaling when you need it most. And finally, simpler API options, and I'll show you the back of my shirt. That's what a command looks like in MongoDB. You just type db.thething in the language of your choice. You don't have to cons up and use stircats and get all together and figure out how to write in a language that you never actually thought was that great. Mathematically pure, mathematically awesome. And by the way, we support a SQL interface as well, but we find people prefer not to use it once they learn. Enterprises today cannot outsource their innovation. Enterprises during COVID, with MongoDB, our experience has been that they are insourcing their innovation. And when they insource their innovation, they want to move fast. Because it's one thing if you can't scale. It's another thing if your competitor beats you to market. So people are trying to figure out how can they iteratively develop their apps for their business faster and faster. So I'm going to sum up and leave lots of time for questions because I've said some pretty controversial things. Is relational the new COBOL? Well, I already said the thesis is it is. Let's revisit. But first, let's think about why some technologies endure and others don't. So on the right, you have things, horses for work are gone, 8-track tapes are gone, blimps and zeppelins, slide rules. Why did they vanish? They vanished because the thing that replaced them had low switching cost and was markedly better. Now let's look at the things on the left. Arguably, in the US, not in Europe, but in the US, railroads are going down. Capacity is going down at about 3.5% per year in the United States, even though the population of the United States is going up, and even though the shipping volume of the United States, thank you, Amazon, is going up tremendously. Lotus Notes is still around. They still use it at IBM. IBM mainframes are still around. Why are they still around? Wait, what's going on? Coal is still around. They're around because of economics. The switching costs of moving off this technology are so high and so scary that people stay with them. So why is COBOL endured? It's endured because it still works. I mean, even though I made fun of the New Jersey unemployment application system earlier in this talk, it still works. It actually ended up processing all those applications. The switching cost is not there, and it avoids the risk. So, could relational have the same characteristics? I don't know. Developers are pretty clever. They could figure out what to do. I've actually seen people use relational stores where they tie together the app and they treat them like key value stores. People could certainly do that. What will the cost difference be, and will it be less than the switching cost? And the key thing to realize here is this doesn't just apply to relational and COBOL, which was meant to be somewhat controversial and snarky. It applies to any decision you're making at your company about moving ahead with technology changes. So longevity is possible, but not assured. I do know one thing. The data flood will continue. And it will continue with this ratio of non-structured to structured data. Now, this conference's sponsor, who I used to work for, believes that we should have a different database for everything. And in fact, Adam today put up a slide with 10 different databases. We strongly do not believe that. We strongly believe that writing applications where you can put your data in one, maybe two spots, maybe one for OLTP and one for analytics, and writing applications which process that data together is so important to the thing which is important for your company, which is being able to process all this data in ways deeper than you've ever been asked to process it before, in ways faster than you've ever been asked to process it before, and at higher volumes than you've ever been asked to process it before. So what are the possible futures for relational? People could continue with it. People could run multiple databases. People could migrate the data when they're ready. We see that happen all the time. Or people could offer SQL compatibility on top of their stores. And we see all of those different things happening. So is relational the next COBOL? It's just economics, just like all the technological changes that you're facing in your organization. And here's a fun question. Did they see it coming? The articles around the time of 1910, 1905 that I researched for this talk said no. They actually thought that cars were this ridiculous thing that was never going to transform. Horses were reliable. There was entire infrastructure around them, and they didn't see it coming. And I think that's kind of where we are today with relational. Thank you very, very much for your time today. And I am happy to take questions from anyone. We don't have a mic, but it's a small room. And I will repeat the question for the live stream, and if I don't, let me know. Questions?
What if the blob gets too big? What if it gets above and beyond MongoDB's
So you're saying, so the question is, what if a document gets too big? So So you're talking about the document limit? So the question is, what if your document gets too big? And that is a real problem, by the way. So MongoDB supports 16 megabyte documents. Dynamo supports 400K. I'm not really sure what some of the other people out there are. What we have found in our experience was 400K is way too small. There's a lot of really valid use cases for storing more than 400K together. But 16 meg is big enough. We have one or two customers that have really wanted to store 32 meg, and we've talked to them. But in general, we don't see that happen in real business applications. It's certainly theoretical possible, and what we see people do is they chain two documents together. Kind of suboptimal, but for all of the other queries, that 16 megabyte document size is pretty good. Next question? Scream them out. Absolutely.
But speaking to the horse and car analogy, in those times where relational was successful, if you had non-relational at the time, would it have just been that much better? Would it have just been like a car or horse by night and day?
That's actually a great question. So the question is, during my time with data through my career, I've seen all sorts of things. And were there times where relational was the right thing for the time? And the second part of the question, if I understand correctly, is what if non-relational had been around at that time? And so the first question is, I actually think the world needed to go through a maturing phase of understanding that data and data structure was really important. So I think in the 80s when I was at Oracle, it was magical watching enterprises actually decide to treat their data carefully. And so that was really cool, no doubt about it. Now your next question I hadn't thought about, which is, if non-relational had been there, I actually don't think so. I don't think it would have taken over, and here's why. Because the computers were actually just scaling at 2x per year, and you could just be lazy, and you could do it. Now, there's one caveat I'll give to that. That's the data size part. Relational has always been hard to program against. Now, I don't mean sitting at the console in SQL Plus and typing select. That's pretty awesome. We all get that. But I'm talking writing enterprise-level applications where you're coding in C or Pascal, God forbid, or some other language where you're trying to do stuff. SQL's always been really hard to program against. So yeah, I think that relational had its time and was really good, and in fact, I was part of that. Next question. So that is a great question. The question is Atlas the next generation of Mongo? So it's really interesting. we're a little company. We have like 2% market share. We're growing very quickly. And so Atlas is the managed cloud service for the MongoDB database, is how it was launched. 5 years ago this summer, so 5.5 years ago now. And that was its first thing, to manage the MongoDB database, just like RDS manages Postgres and MySQL. Now, RDS doesn't do anything to Postgres and MySQL. It manages them in a very hands-off way. With Atlas, we've actually gone a step farther. With Atlas, you can actually, we've made changes to MongoDB to make it much more manageable, which is kind of awesome. MySQL and Postgres certainly haven't, okay, because they're not sure they want to be managed. In fact, the Postgres community has kind of a love-hate relationship with Cloud SQL and RDS, to be quite honest, okay? And then we've also added analytics and search and Realm mobile to allow you to have one application platform that you can program against in Atlas. And so it's actually much more than a database management program. It's an application as a service platform. So, sorry that was a little brandy, but that was kind of a full answer to your question.
No, absolutely.
Do you have a follow-up?
Yeah, I have a follow-up. So the question is, so you mentioned that Atlas multi-model, or maybe it's a general purpose, wide purpose use. So does it also mean that with Atlas, Elasticsearch and things like Solar is also becoming obsolete?
So the question is, if Atlas is becoming a multi-model database, as I've talked about here today, and by the way, this is not a MongoDB product pitch. Other NoSQL databases have a lot of the same properties I've talked about today. They're not as good as the one I happen to work for, but they do. So, I mean, a lot of what I talked about today is just about NoSQL versus relational. It's not about MongoDB. Now I'll take it to the next level. The rest of the question was, does this mean that Elastic and Solar and things like that are obsolete? Well, I'm going to tell you right now, I sure hope so. We tied together Lucene directly into the database engine, and it sits right there beside it. So you don't have to copy the data, despite all the diagrams you've seen of all these arrows copying data everywhere. You don't have to do that in our system. And I imagine other people will emulate that over time. So no, you can actually do search and search indexes directly on the data. Now, Elastic and Solar are great products for what they do. If you have a system where you haven't integrated Elastic and Solar, like we did into the database, then yeah, Elastic and Solar are going to continue to run. And there's going to be phrases where people are putting Kafka data as fast as they possibly can into Elastic and Solar systems and running it on them. So we have a demo that we showed in London, actually, where in about 5 minutes, they take an app, they turn on Lucene, it indexes, and they modify their app, and in 5 minutes, they're doing queries in an app against a live search index. So it's kind of cool. And again, you'll notice the thing I keep talking about is speed of developing apps. Because if you develop the app fast, you can figure out what you got right, and you can figure out what you got wrong, and you can deploy v17 and v18 and v19, and you can pivot. There are many companies I've talked to, both at Oracle and at RDS when I was there, and now, where I ask them how often they roll schema. I heard some snickers. Rolling schema means rolling a new schema into your production database with new columns and things like that. And most C-levels I talk to go like this, and they say, maybe once a quarter. And what does that mean? That means that those new columns, which hold the new data, which hold the new features for their new application, are gated by their IT department only letting them roll new schema once a quarter, which means that their speed of innovation is fundamentally limited. So, long answer to your question. I chose to get on a little speaking podium there. Next question.
Would you say a lot of this is driven by the fact that we need to deploy and build applications much quicker and be much more agile than, say, the past when they had to be super efficient with their programming because of the limits of storage and resources?
So the question is, would you say that a lot of this is because people need to deploy apps faster and differently than when people were really focused on efficiency? Yeah, I think that's the case. I mean, I remember when I used to write programs where we were sitting there laying out the records and laying out the bytes and saving bytes here and there, and we were stacking bits in UB8s, and we were trying to be so clever. Well, that kind of cleverness is not what's important today. And I had a slide on this in my talk I deleted, which was what used to cost money was computers. What used to cost money was storage. There's two things that cost money today. One is your developers, who, as a result of COVID, developer salaries are going up quite strongly. And second, do you know what costs more money? Being second to market. And that's what really costs money. And so, yeah, I think a lot has changed where the speed of innovation and the speed of experimentation, which is given to you all in non-database ways by the cloud, hosted by our wonderful sponsors, or by AWS, is great. And then we want to offer you that exact same speed of application development against your persistent store. And notice I didn't say database because there's different kinds of persistent stores out there. We want to offer you that exact same speed of development. And frankly, persistence, in many ways, is a lagging area of computer engineering for the ability to program and do things quickly and efficiently. So yeah, I do think a change has occurred. And I think there's a question down here. I do think a change in the industry has occurred that makes this more reasonable. Okay, we got about 5 more minutes. We don't have to take any more questions. I see. Oh, yes?
What do you think are the myths for people to be afraid of moving on?
I'm sorry, can you repeat the question?
What are the misses, in your opinion, of people afraid of moving from SQL?
What are the misses? Myths of people moving. Well, okay, so the reality is you got to learn a new skill. Let's be clear. Programming against a non-relational database is different than programming against a relational one. Another myth is that it's not performant. That's not true. I talk with customers who are running 1 million transactions per second on 400, 800 terabyte databases all the time. Amazon Aurora tops out at 64 terabytes, guys. Okay? So one of the myths is that NoSQL is not mission critical ready. Banks use it, distribution systems use it, cryptocurrency exchanges use it. So that's myth 1. Myth 2 is that SQL is a better way to program. And I gotta tell you, when I came to this company, I was planning on talking to Dave over there and saying, we really, really need to offer SQL. And I kind of felt that way for about 6 months until I started looking at sample programs. And I started looking at just how hard it was to program using SQL versus modern databases. And so that's another myth. Those are the only 2 that come to mind right now. But yeah, those are 2 of the myths. A, that it's really hard to learn. It's not. B, that it's not mission critical. So I guess that's 3 myths. And C, that you have all this stuff that just isn't ready for prime time. Okay?
You mentioned storing data in 2 places, one for analytics and OLTP. Can you talk more about that?
Oh, so this is hard. So the question is, I'd mentioned talking about storing data in 2 places. And I am going to be very transparent here. This is something that we in the data industry are really thinking about. So MongoDB has an OLTP store where you can do light analytics. We have a data lake store where you can do much heavier analytics. Other companies try to merge those 2 things together as well. Oracle has a column store. I mean, if you don't mind paying Larry Ellison, has the ability to do both. The reality is, I think what you need to do is start with the customer. What questions are the customer trying to ask? And if the customer is trying to ask, the developer, a real-time question, should I let this transaction through or is it fraudulent? What recommendations should I put up? That kind of analytics, I absolutely think belongs in a real-time store. No doubt about it. The kind of analytics where I'm trying to figure out what the trends are in Indonesia for people with a certain demographic, I'm just struggling that belongs in a real-time store. The reality is that there's a reason S3 exists. It's cheaper to store data in S3. It's slower, which is fine, but it's good enough for those analytics queries, like we offer our analytics. I don't think people want to pay for local NVMe to answer analytics questions the vast majority of the time, and I don't think people can afford to wait for S3 if they need to issue a fraud verdict in 90 milliseconds. And so that's really the challenge there. So I do believe that there's 2 stores. Over time, we'll have a better point of view on that as a company.
What's the kind of data encryption that
I'm really sorry, I can't hear you. Can you come up closer?
what data encryption methods do you support?
So we support, I don't have the list, we support all sorts of encryption, all the way down at the core level, network encryption. We support a special kind of encryption, which really no one else does, which is it's called client-side field level encryption. And the beauty of that is maybe you don't want to trust MongoDB. Maybe you don't want to trust your cloud provider. You can keep the keys on your side, on your client machine, and the data is only ever encrypted in the server. So even if an AWS operator or a MongoDB operator or an RDS operator tries to look at your data, they can't. So we support encryption at rest, encryption in transit, and even encryption fully in the database where it never gets unencrypted. And by the question, I forgot to repeat it, was what types of encryption do you support? So if you go to mongodb.com, you can see all that. Okay. One last question. Maybe there's others coming. We still have 4 minutes.
The question is, you mentioned Oracle and SQL and DB2. So many of these databases and in many companies have lots of data as well as lots of code and stored procedures. Now they are like, I've seen 5 to 7 pages of stored procs with business logic in it, all across the organization. So as a part of modernization, do you have some thoughts on how does that thing get into the new world?
So the question was, there's a lot of people out there with Oracle PL SQL, founded by my friend Peter Clare. There's SQL Server T-SQL. There's DB2 with its stored procedures. How do we move those into the modern era? And I'm just going to have to say, there's no magic. There are programs out there that are produced by various people. I believe there was one launched today by AWS. The reality situation is it's hard. The view of the world was that we should put everything close to the data. What people missed was that we actually wanted to have the logic close to the programmer. And so there's no easy answer there. There's just dig in and do it. Now, what we have found is that as you talk with customers and you help them transform 2, 3, 4, 10 apps, by the end of transforming that small handful of apps, they are more experts on transformation than we are. And so our job is not necessarily to transform people's apps, but to teach them how to transform and help them on the journey. And then they come back with all their own roadmaps for doing it. We had a customer with 1 million lines of PL SQL. It was a 3-year migration. Okay.
One question. What would you recommend to teams or companies who are so coupled with transactionality and multi-transactionality, and then mental consistency is just not something that you like to embrace?
Wow. So the question is, what would you say to teams who are just coupled with eventual consistency and aren't sure about embracing, or who are transactional and aren't sure about embracing eventual consistency? Maybe there's something I forgot to mention. MongoDB is fully ACID compliant, even across a multi-shard cluster. So you can run your transactions with full majority ACID compliant, and you can run them with lower level consistency, something you can't do in some other systems. And so I should have brought that up. There was a question out here about myths. One of the myths is that non-relational doesn't support ACID transactions. MongoDB absolutely supports ACID transactions. I mean, for God's sake, we run banks. And so that means we do support ACID. We run cryptocurrency exchanges. So to people who are struggling with moving from transactional to non-transactional, I'll say you don't have to. Now, the reality is, Einstein was not our friend. The speed of light is not very fast. And if you are going to do a transaction which has to commit across multiple machines or across multiple parts of the world, you have to pay the piper. We give you the ability to either pay the piper or to say, no, this is a log write or a click write, and not pay the piper, just fire and forget, or the ability to run it if it's actually movement of money between 2 accounts, as an example. You can run it with full ACID compliance. So, okay, and with that, I think I'm going to wrap up for today. I have truly enjoyed the research I did for this paper, and I really hope you guys enjoyed some of the insights that I gleaned during my months of prep. Thank you very much.